For our final experiment of the semester, we're going to calculate the rate law for a particular chemical reaction, and that reaction is going to be the reaction between iodide ions, bromate ions, and hydrogen ions, forming elemental iodine, bromide, and water. Now, the rate of a chemical reaction is always proportional to two things. It's proportional to the temperature, because if you increase the temperature of a reaction, you're going to cause the reacting molecules to bump into each other more often because they're moving faster. And if they bump into each other more often, that's going to cause a faster rate of the reaction. The second thing that will cause the rate of the reaction to change is the concentration of the reacting molecules or ions, because in this case, if you increase the concentration of iodide or bromate or hydrogen ions, then once again, they're going to collide with each other more often, and that'll cause the reaction rate to be faster. So our algebraic expression that shows these two facts, the fact that the rate is proportional to the temperature and the concentration of the reacting molecules or ions, is called a rate law. And this is what we're going to try to determine in part A of the experiment today. Now you can write a skeletal rate law for any chemical reaction, and that's going to demonstrate the two facts we've just talked about. The rate of the reaction is going to equal a constant. Well, that constant depends upon temperature. So if temperature increases, that constant will increase. And the rate of the reaction also depends upon the concentration of the reactants in the reaction, and I have them all written here. And essentially, to solve for a rate law, you have to determine the exponents for each of the reactants. And so we're trying to solve for x, y, and z. The technique we use to do this is we actually do a series of experiments where we're starting a reaction with various concentrations of the different reactants. And today we're going to actually do 4 different reactions. We're going to have reaction mixtures 1, 2, 3, and 4. And those 4 reactions are going to have varying concentrations of iodide, bromate, and hydrogen ions. If we look at an example for as reaction mixture number 1, what we're going to do is we're going to have 2 different flasks, flask A at the top, flask B at the bottom. In flask A, we're going to put the iodide ions, but in flask B, we're going to put the other 2 reactants, the bromate and the hydrogen ions. That way we keep them separated until the instant we mix the 2 together, and then we can start timing to see how long it takes the reaction to occur. So what we're doing is we're going to be mixing 5 milliliters of potassium iodide, 5 milliliters of sodium thiosulfate, and 5 milliliters of water together in flask A for reaction mixture 1. That's 15 milliliters. And then eventually we're going to mix it with the contents of flask B, which is 5 milliliters of potassium bromate, 5 milliliters of hydrochloric acid, and a negligible 2 drops of starch indicator. So that's 10 milliliters. The total volume is going to be 25 when they're mixed together. So the first calculations we have to do is calculate what the actual concentrations of our reactants are going to be when their volumes get all mixed together to a final volume of 25. So these are dilution calculations. So in your data table, the first thing you're going to do is going to calculate what the new diluted initial molarities will be for the iodide ions from flask A, and then from the bromate and hydrogen ions from flask B. In the data table, you notice I'm only giving you 2 boxes to calculate the diluted concentrations of iodide, bromate, and hydrogen ions. And that's because if you look over at the data on the left side, the volumes of iodide that are used are either 5 milliliters or 10 milliliters, each being diluted to 25. So you actually don't have to do 4 calculations because in this case, 3 of them would be the same. You're just going to do 2 calculations, the dilution of iodide from 5 milliliters to 25, and the dilution of iodide from 10 to 25. And similar things happen for the bromate and for the hydrogen ions. So once we've calculated the initial concentrations of all of these different reactants, we're going to mix them together and time how long it takes the reaction to occur. And we're going to measure the temperature because what's really important is we have to make sure that the temperature remains constant for each of these different reactions, because if the temperature were to change, that means our numerical value of K will change. And here's why this is important. To calculate the values of X, Y, and Z in our rate law, we're going to use the technique where we're going to divide data from one trial with data for another trial. So if we take data from one reaction mixture and we plug it into the rate law, we won't know the values of X, Y, and Z or K, but we'll know the rate and we'll know the initial concentrations of the 3 reactants. And we divide it by reaction data from another mixture, same thing. As long as the temperature is the same, the Ks will cancel out. And then we can actually, and if we keep 2 of the 3 reactants constant, their concentrations will cancel out. And we'll be able to see how the rate is affected by one of the particular reactants raised to its particular exponent. And we can solve for that exponent. Now, in the experiment today, you'll see in the video, they're actually measuring how long it takes the reaction to occur. And time is not the same thing as rate. If you live, let's say, 30 miles away from Saddleback College and it takes you 1 hour to drive here, that time, 1 hour, is not how fast you're going. How fast you're going, we usually express in something per time. For driving a car, it's miles per hour. So if you're driving to school and it takes you 1 hour to get to school and you know you live 30 miles away, you have to take the reciprocal of that. So if you go 30 miles per 1 hour, that's your rate. So what we're going to do is we're going to take whatever the time length is for the reaction to occur, maybe 30 seconds. We'll take the reciprocal of that because the units will be 1/seconds, and anything per seconds is going to be something proportional to the rate. I'd like to have molarity in the numerator, but I don't know the molarity. So what we'll just do instead is we're going to make up a number of 1,000 to put in the numerator. We're doing a big number like that because that's going to make the numbers more easily written in the data table. Otherwise, it could either be really, really big or really, really small. So that's just sort of arbitrary. But the important point about calculating the rate is we're just taking the reciprocal of the time, because rates are always proportional to the reciprocal of how long a process takes. So you'll have all the rates calculated in your data table. You'll do these divisions as we have shown at the top of the slide, and you're going to be able to calculate the rate law. And the important thing in your rate law is going to be that you calculate the values of X, Y, and Z. So I want to see what those numerical values are. Once you have the rate law, you're going to calculate the value of the rate constant from all 4 of the reaction mixtures, and then you'll average those together, and you'll get the average rate constant for the reaction. And that's what we're doing in part A. In part B, we're going to try to calculate the activation energy of the reaction. And to do this, we're going to have to perform the reaction at different temperatures. And so the video today is going to perform the same reaction at 0 degrees, 20 degrees, and 40 degrees. And we're going to all do reaction mixture 1 3 times in a row. So we've already calculated the initial molarities of iodide, bromate, and hydrogen ions. So we don't need to do that again. That's why it's not in the data table. But we're going to measure how long the reaction takes at 0 degrees, and then at 20 degrees, and then at 40 degrees. Now, those are approximate temperatures, 0, 20, and 40. We'll actually have a thermometer and we'll measure the actual temperatures. So we're going to put that in the data table. We'll switch that into Kelvin, and then we'll take the reciprocal and go 1,000 divided by that time length to give us the rates. So we're going to have rates at 3 different temperatures. Now, what's important is we're going to want to calculate the specific rate constant at each of those temperatures, because as we said at the beginning, the K in the rate law is proportional to temperature. So when the temperature changes, our constant should change. And so we're going to calculate from the rate law we calculated in part A and the numerical value of the rates we've just calculated here and their initial concentrations. We'll calculate the rate constant at 3 different temperatures. We'll then take the natural log of that, and then we'll take the reciprocal of the temperatures. The reason we have and I didn't put a little calculation boxes for those, because you're just going to press a button on your calculator to determine the natural log of K and the reciprocal of the temperatures. But the reason we do that is that Arrhenius had to derive an expression showing how the specific rate constant for a chemical reaction at a particular temperature can allow us to determine the activation energy. Arrhenius proposed that the natural log of the specific rate constant that you calculate from a rate law equals negative E sub A over R multiplied by 1 over the temperature plus natural log of A, which is a constant. So if you notice this expression fits the form y equals mx plus b, that means the slope of the line is going to equal negative E sub A over R. So you're going to plot the 3 values for the natural log of K versus 1 over T, and then you're going to actually have the computer calculate what the line of best fit is and display the equation for you. Once you have the equation displayed, it's going to tell you the slope, so you're going to know the value of m. So once you know the slope for this line, if you just multiply the slope by negative r, you'll be able to calculate the activation energy for the reaction, and that'll be our final experimental calculation of the semester.